Good morning, everyone. My name is Maleah Rhem, and I am a senior at the University of Alabama in Huntsville. This summer, I worked in the CCA with Caitlin Breivik, and this summer, we were cooking up binary black hole mergers. So, a little bit of background information about gravitational waves before I get into BBH mergers. Gravitational waves are ripples propagating through space. Some of their sources are listed here, but we like to study the merging black holes in our research. Basically, these waves tell us about the bulk movement and the distances to their sources. And also, studying them helps us understand a little bit more about the source origins of their sources. So here in this animation that you can see on this slide, we have two merging black holes. And when they merge, you can see all these gravitational waves that are being emitted from them. Now, currently, there have been nearly 100 gravitational wave events detected by the LIGO-Virgo-CAGRA collaboration. And here on this slide, here are two events from the 100 events that I mentioned before. These are both binary black hole mergers, and listed for each one are the black hole masses and the distances to them from Earth. Now, the first one is 150914. This is actually the very first binary black hole merger detected by LIGO. And the second one is our event of interest that we looked at in our study. This is 1911-29, and it's an event from the GWTC3 catalog. Now, as you can tell from looking at them, there are some differences in the black hole masses. And we believe that because 1911-29 has lower black hole masses than 1509-14, we also think that it has lower mass progenitor qualities as well. So there is a problem. First, it's that producing BBH mergers is very difficult. And to explain why, I'm going to go through how we get these BBH mergers by explaining some steps about binary stellar evolution. So first, we start out with our binary. We have two stars orbiting each other. And this is representative of 100% of zero-age main sequence binaries in the universe. And you can see the progression of their masses as we go along. Next stage in evolution is that the primary star goes into what we call Roche lobe overflow, where it expands past a region surrounding it. And then the envelope of this star is no longer gravitationally bound to it, and it is accreted by the secondary star on the left. Out of 100% of binaries in the universe, only 70% of them survive this first Roche lobe overflow and stop at this point in the evolution in Hubble time. Next stage of evolution is that after the envelope of the primary is stripped, you're left behind with the core, and eventually it will collapse into itself to form a black hole. And out of 100% of our binaries, only 7% of them survive up until this point. Next part in our evolution is that the secondary star goes through the same stages that the first one did to form a black hole. And out of all binaries in the universe, only 0.2% of them survive and stop in their evolution at this point. And then eventually, after we are left with our two black holes, we get a merger, which produces a gravitational wave event. So out of all binaries in the universe, only 0.02% of them are actually close enough to merge in Hubble time. So as you can tell, takeaway from this figure is that it's very difficult to produce these mergers. And one of the biggest uncertainties is what happens during Roche lobe overflow that produces a merger in Hubble time. First thing we like to think about is the common envelope phase. And the common envelope is an envelope of gas that surrounds the binary system due to the unstable mass transfer from the primary to the secondary. Usually all of the orbital energy and the angular momentum from this orbit is lost in this envelope. And what we need for a successful merger is the ejection of this envelope. We need it to go away because as you can tell on the picture on the right, at the little circle on the left side of the picture, once we eject that envelope, we get two black holes that do merge. But when we don't, on the right, we get a stellar merger, which is not what we want to look at. Second channel that leads to a merger is the stable mass transfer, as I've already spoken about before, which is basically just the transfer of mass from the primary to the secondary. So, like I said, it's very rare to see these binary black hole mergers in the age of the universe. And we want to look at more gravitational wave events from them. So, what we want to figure out in our research is what is the recipe for producing these BBH mergers? So, here's how we figured out how to find more of these mergers. First, we started out by simulating binary populations of an event that I mentioned before. We simulated progenitors of GW 191129 to determine the recipe which produces mergers similar to this event within Hubble time. And we did this using COSMIC, which is a binary synthesis code that produces large binary populations. So, what do we need to see in our data for a successful BBH merger? Well, first, we need the perfect combination of these two variables. The first is the ejection of the common envelope, like I mentioned before. And this relies on a variable called alpha, which is our common envelope efficiency. Next thing that we need is the shortest orbit possible after stable mass transfer, which depends on the fraction of mass accreted by the accretor. And we like to denote this as FAC. So in our box here, what we need from these two variables is a low alpha, because this will have more orbit shrinking. And we also need that our FAC need to be less than 1 so that our orbital separation widens less during mass transfer. So in a lot of studies that we've seen before, they fix both of our variables for the whole population. But Kays Wong and his team here at the Flatiron Institute developed a method where we can look at all possible values for alpha and for FAC so we can find every possible recipe for these gravitational wave events. And here on the screen, you're seeing a simulated population for GW 150914. These are zero-age main sequence mergers for this event. On our x-axis, we have our primary masses and solar masses. And then on our y, we have our secondary masses. At each top of the plot, we have both of our variables. We let alpha take on 3 different values, and then we let FAC stay fixed. But then in the last plot, we let both variables vary because, again, we want to find every possible recipe for these mergers. And also, what you're seeing in that color bar is our count density. So in our study that we looked at this summer, we wanted to figure out what is the recipe for producing GW 191129. This is our event of interest again. And here's what we found after simulating our binary population for our event. So at the top, we have GW 191129, and it has the exact same setup as 150914. We, of course, included the one at the bottom just for reference, because again, the method has already worked on this one. At the top, you can see that for 191129, it prefers a mass range for primaries between 25 and 60 solar masses, and 12 and 50 for secondary masses. And also, main difference between these two is that 191129 prefers a much lower mass range for progenitors than 150914. Now, if you take a closer look at the plots at the top, you can see that we're seeing some higher mass progenitors that we're not seeing in the other 3 plots. And what we wanted to figure out is what specific values of alpha and FAC are producing these higher mass progenitors, because it's very difficult already to make binary black hole mergers from masses of this size. So that's what we wanted to examine even further. So what we did is we took that little plot and we plotted alpha versus FAC for 191129 for the lower mass range and the higher mass range. So on the right, you can see the variables plotted against each other for our lower masses. And as you can see, for alpha, it varies a lot. But for FAC, it prefers a very specific value of close to 10 to the 0th or 1. But however, when you look at the higher mass progenitors, you're getting a very specific range for FAC and for alpha. So what we now know is that when we want to look for more massive progenitors that produce these mergers, we need a moderate FAC and a very low alpha. And we wouldn't have found this result if we did not let our variables vary in our study. So overall, what did we find? First, we found that for GW 191129, it prefers a specific mass range of progenitor masses before mergers occur between 25 and 60 primary masses and 12 and 50 secondary masses. We also determined that it has a much lower mass range than 150914. We also found that when we allow our common envelope efficiency and our accretion limit, alpha and FAC, to vary, it produces a wider range for progenitor masses for 1911-29. And we also saw that this is much similar to 1509-14, thus verifying that our method is in fact working. Also, when we took a closer look into those higher mass progenitors, we found that it prefers a very specific range for FAC and for alpha, with FAC being in between 0.1 and 0.32, and alpha being less than 0.32. And again, to re-emphasize, we would not have found this result if we did not let both of our variables vary. So overall, from our research, we have verified that the method that we used worked. And for future research, we want to look for more progenitors with parameter spaces different to the ones that we use for 1911-29. And hopefully this will lead to the interpretation of more binary black hole mergers, and hopefully we can look for more gravitational wave events. And that's it for my talk. Thank you for listening.
All right, any questions from within the room for Maleah? Yeah, Sam?
Thanks. That was an awesome talk. Oh, can you go back one slide, maybe? So I was just curious, once you determine the best FAC and alpha values, is that to make the people who are kind of looking for these events change the parameters for the events they're looking for? Or is it that after you find an event, you're able to kind of like process them differently?
Right before the event is what's best. And that's what makes the finding that we found so interesting, because again, just to reiterate for like the third time, if we didn't let them vary, of course, we wouldn't have found those for the higher mass progenitors, because they're already very rare, and the rarity of it increases when we increase the masses of the progenitors. So yes.
Other questions from Maleah? Is there anyone on Zoom that has a question? If so, you can unmute and ask. Okay, I actually have a question, and that is, at the beginning you showed the statistics or some of the information for these two events, and 1509-14 seemed like it had much higher masses and it was much closer.
Yes.
And then the one that was your one of interest had lower masses and it was farther away.
Right.
So does that mean, was the detection signal, was there more noise in 1911-29, and did that affect any of your work, or?
I'm not sure, because I actually didn't examine the actual gravitational waves. I just looked at the progenitors before the merger occurred, so I'm not actually sure right now. But yeah, I don't know.
Okay, yeah. All right, so let's thank Maleah again.
Thank you.